genomes are sort of like mosaics. They're just full of stuff that looks like it's bacterial and viral DNA all patched together. So that makes it really look like we're sort of an accumulation of viral information. So this is revolutionary, and if it's correct, it's certainly wonderful to propose a complete alternative. And it does explain punctuated equilibrium, and it would leave this model completely, if Maximo is right, Darwin is completely wrong, and this model is of value mathematically perhaps, but doesn't have much connection with real biology. You know, those are the breaks. I mean, you're a theoretician. Sometimes your theory is relevant to the real world, sometimes it isn't. It still is a piece of pure mathematics that may or may not be of interest.
So up to this point, you cannot say this model is better than this one.
I can't
based
say.
on this guy.
It's not clear. Much more work is needed. This is just the first step. If we're lucky, this is the first step in a promising research direction. If we're unlucky, it's not even that. But I think, you know, especially now that you're coming from a different perspective and looking at this and says it looks reasonable to you, I think we have a reasonable case to think that this is a line of research that should be pursued. But the work has to be done. And we may find out that Darwin's theory is wrong. And of course, Maximo won't be surprised. He's been saying that for a long time. So here in Madrid. And I just ordered 3 books of his from Amazon.España. So that won't be a surprise here. So the answer is we don't know.
Yeah.
What about hierarchies?
Oh, thanks for asking that. Okay, if you look at the key chapter of the book, chapter 5, Proving Darwin, which was the Santa Fe lecture, and if you look at my technical paper, Life as Evolving Software, when I started working on this, one of the things I wanted to get out of my theory was hierarchical structure in organisms, right? Because that's a very basic feature of living organisms. And after I got this model and was able to sort of characterize its scaling or how it works, I don't know what to call it, I, of course, was rather pleased that I was able to prove something about the behavior of this model. But then I looked back and I said, well, are these organisms hierarchical? Do they exhibit hierarchical structure? Well, not really. I mean, you're adding bits onto the lower bound on the, but it doesn't look too, the program, that's data. The program, the part that is algorithmic in each of these organisms that makes this thing work, is fixed. It's just this standard program that takes this lower bound of the halting probability and converts it into a very large number. So there doesn't, so whatever the level of hierarchical structure in that program is, it's constant. Okay, so that, of course, is disappointing. However, there is a way to get hierarchical structure out by considering a different model, because there are lots of models of this kind that are possible. So what I did was, I said, okay, let's not use the programming languages that algorithmic information theory uses, which are very sophisticated. Let's use a more primitive kind of programming language, one, in fact, that is not universal, that cannot express every possible algorithm. And it's a very natural programming language. It's the first programming language I learned as a teenager, in the days when most teenagers, you know, computers were enormous, and most people did not get to program computers. And I was lucky that as a teenager I was able to get to use big mainframe computers where you had to punch cards, and so Fortran was the first language that I ever programmed in. It still exists, and at least in the original version of Fortran, there is no halting problem, because before you go into a loop, you have to decide how many times you're going to do the loop. You know the number in advance. So you can bound, you know, the programs are always going to halt. You can't really write you get rid of go-tos, right? Nobody likes go-tos, right? The programming language had go-tos. But in the toy version I'm going to use, but you know, it was always a bad idea to use them because you end up with a program that's spaghetti. So if you throw away being, you can make a simplified version of Fortran, and as theoreticians did this in the 60s, I think it was, Ritchie and Meyer published a paper with a thing they called loop programming language, which is a very simple programming language, where there's no halting problem. And so I take this as the programming language of my organisms. Now, what is the fitness function? As the mutations, I'm going to keep these same mutations. you don't have to pick the same programming language for the organisms and for the mutations. Okay, so I stick with the same mutations I have in this model. They're very powerful. But the organisms now will be a more primitive programming language. Now, what is the fitness function? Okay, these organisms here want to calculate a single big number, positive integer, and stop. The organisms in this primitive programming language want to calculate a function. And it'll be fitter if the function goes to infinity more quickly. So they're given as input one integer, and they're going to produce as output another integer, and an organism will be fitter than another organism if eventually, from some point on, its output function is bigger than the output function of the other organism. And you can get situations where things oscillate, and you have two organisms, neither of which is fitter than the other. Okay, if you do this. Okay, so now it's a function instead of a number that the program calculates, and you need an oracle. Even though there's no halting problem, the program will always halt, but we're talking about functions, so you need an oracle to decide, given a program, if one of them is fitter than the other. So again, if I have an organism, it calculates, it calculates n squared, or n to the n, or n to the nth. It's a function now of n. It's given n as an input, and it's going to calculate. And I try making random changes to see if I get a program that calculates a function that goes to infinity more quickly. Okay, so it'll be n squared, n to the n to the n to the nth times, that kind of stuff. And this is the kind of stuff you can program very simply in this loop programming language. And now you can prove very easily that the nesting level, these programs, their hierarchical structure is, if you have loops that are n levels of nested loops, that's n levels of hierarchical structure. That's the hierarchical structure this programs can have in this primitive language. There are no subroutines. There's just a main program. So hierarchical structure means that you have more deeply nested loops. And it's very easy to prove using results of Meyer and Ritchie that in fact the loop nesting level will very quickly go up and will never go down. And it'll get higher and higher. Because it turns out that for every, there's a hierarchy of programs at each level consists of programs which have exactly maximum loop nesting level k. And it turns out that in this hierarchy, the next level always has a program that grows more fast than any program in the levels below. So once you try that, once you try a mutation that does that, then the loop nesting level will never go down. Now there is a mutation, the smart mutation in this system is very easy. It's one that, given a program, it has no parameters, it's a single mutation. So it's going to be tried very frequently. What this mutation does is, given an organism, it just looks to see the maximum loop nesting level in the current organism. And then what it does is there's sort of a standard program with one more loop nesting level that grows very fast, that grows faster than anything with a smaller number of nested loops. It just produces that organism. So you have a single mutation that is driving the process forward. You don't have an infinite, there's no parameters. So this smart mutation will be tried on the average very frequently, right? If it's k bits long, it's going to be tried 1 over every 2 to the k tries on the average. You're going to try that, and you're going to drive the loop nesting level up by 1. In fact, the loop nesting level will shoot up even faster than that. But anyway, the point of this model, I actually prefer this model. I think this model is deeper mathematically. But the other model is also good because it shows there are ways to set up models of this type, and maybe that model in fact is closer to real biology, because the programming language is as powerful and the amount of time involved in the computations is more reasonable. The mutation is not an immensely sophisticated one like here. It's a relatively fast computation. So in a way that's more closer to real biology, and you are getting hierarchical structure emerging. You see, so I regard that as an encouraging sign, and thank you for asking. It is an encouraging sign. Hierarchical structure is really a key feature of biological organisms, and any theory that doesn't get that out, a theory of evolution that doesn't show you that is going to happen, with high probability, is a bad theory of evolution, because this is a piece of observational data of empirical data that we all have. So there is at least that one case where you can say it's not a question of the rate of evolution, but we have this match with one very basic feature of the organism we see all around us, which is that they have hierarchical structure. You see, so that is, thanks for asking. That is I think that's very relevant to your question. I didn't realize that.
We are running out of time and we don't want to tire you more.
Yeah, so if you're interested in all of this, please
No.
start working on it. The field is open.
So, Greg, thank you very much for,
It's been a pleasure.
For your lecture, and it's a pleasure to have you here in Madrid for your first time.
For us too.
In this university.
A pleasure and an honor.
And, well.
And Virginia continues tomorrow. It's not over yet.
Yeah. So
For dessert, she's going to really give an overview of all of this from a philosophical perspective, but she's going to look at the main features of what we've seen. In a way, it's a way to summarize everything we've seen before. So it's a good way to try to fix in your mind the main features of everything I've done in these past 3 days, and what are the main features of the whole enterprise. So you might find it interesting. It's not technical philosophy. I mean, it's down to earth. Thanks very much.
Thank you. So, as Professor Chaitin said, that tomorrow there is the last chapter of lecture of this cycle, and it will be given by Gregory Chaitin. And the title, well, is about the metabiology and methodology.
Methodological consideration
Consideration and
philosophical interpretation.
philosophical interpretation. Okay.